Hi, everyone. Today we'll be talking about linear systems and how to use matrices to solve them. So let's start with a definition of what a linear system is and some examples. So an easy example is in algebra, you learn how to solve things like 2x equals 4 or 3x plus 5 is 17. So for 2x equals 4, you just need to divide both sides by 2, and right away you see x is 2. 3x plus 5 is 17 is a little bit more involved. You first subtract 5, and then 3x is 12. And then you divide both sides by 3 to get x is 4. So before you learn how to divide, the above simple problems could be really intimidating, or you might not know how to do them at all. And once the students learn how to graph, on the other hand, students can learn how to use geometric ideas to solve the problems, such as graphing 3x plus 5 is 17, and graphing y equals 17. You could split up 3x plus 5 is 17 into y equals 3x plus 5 and y equals 17, and look for the x coordinate. Here we see x is 4. So you can use graphical methods to solve these algebra problems. And similarly, you could graph y is 2x and y is 4 to solve 2x equals 4. You'll see two lines intersecting at x equals 2. In general, a linear system looks like 1 here. So ax plus by equals e, cx plus dy equals f, where a, b, c, d, e, f are known and x and y are unknown. What makes this a linear system is that we just see x and y by themselves. So there's no x squareds, there's no x cubes, there's no y squared, there's no xy, nothing like that. So the powers of x and y are 1 or 0, and there's no products of multiple variables with x's or y's. That's the important thing. So yeah, we assume A, B, C, D, E, F are known. Otherwise, this would not be a linear system. Like if A and X were both unknowns, that would change this kind of problem. You might have solved equations like x squared is 1, where you take a square root on both sides to get x is plus or minus 1. And that's not the kind of equation we'll focus on. That's not a linear equation, even though that is a valid equation to consider and learn how to solve. And it's important to learn how to solve that too. So for 3x plus 5 is 17, that's one equation. So there's only one equal sign between two things and one unknown. The strategy to graph it was to split it up into two unknowns, like y equals 3x plus 5 and y equals 17. So we could actually think of this one equation we had as two equations if we wanted to, and we could bring all the x's and y's to one side, like we had in what we did above with this one. So if we want to make it look like one, this system of equations one, then we could bring the y over, and now it looks exactly like that. And now we could try to solve this system instead, and the solutions should be the same, where y is 17 and x is 4. So in general, we could call this decoupling an equation. So we take one equation and split it into two equations. So ax plus b is cx plus d is the kind of equation we decoupled, where c just happened to be 0. So if we do this, these two lines could be parallel or they intersect exactly once, resulting in a unique solution for x. And if they're parallel, they might not touch at all, in which there's no solution, or they might be exactly the same line, in which case there's infinitely many solutions. Every single point on the line is a solution. So if you decouple this way, sometimes we obtain extraneous information like a value for y. There was no y we were solving for in the beginning, but now we get y, and y is 17 in this case. There is something much more strange we could do. If ax plus b is cx plus d, then we could instead try to decouple them into a constant instead of a variable y. But this won't work because we're setting an extra restriction. We don't know that that's equal 3. We don't know what it's equal to at all. So this would result in some wrong solutions. Um, if you follow this process. So there's a little bit more in the notes. In general, if ax plus b is cx plus d, then x is b minus d over c minus a. But if you write these equations are equal to 3, or something similar to this, then you get some other solutions for x in both of them, which might not be compatible. Like 3 minus b divided by a might not even equal 3 minus d divided by c. So this way you lose information and you even lose a solution. Another issue that could happen is if you had two equations, ax plus by equals e and cx plus dy equals e, and you forget e exists and you just set them equal, this will be a problem. So ax plus by is of course equal to cx plus dy because they're both equal to e, but this loses information. Maybe e is equal to 5, or maybe e is equal to 3, but either way, we don't know whether ax plus by is 5 or 3 or 4 or anything else, no matter what e we fixed. So we lose the information about e. So what problems it could cause is, for example, if x plus y equals 1 and x minus y equals 1, we could add the two equations to obtain 2x equals 2, and then x equals 1. And when you plug x equals 1 back in, you see that y equals 0 is a solution. So 1, 0 works for both of these equations. So 1, 0 is a solution. But if you forget about 1 and you just set them equal to each other, then you could subtract x from both sides and get y is minus y, therefore y is 0. And then we're left with x equals x, and that's it. We don't know what else happens with x. Before, we knew x equals 1, but now x just equals x, and we have infinite solutions. Anything works. So this causes issues. So be really careful when you're trying to combine two different equations. This chapter will basically be about what methods are legitimate for combining the equations and what language can we use to talk about it. So this step right here, adding the two equations, is actually called the method of elimination. We eliminated y when we added these two equations, and we were just left with 2x equals 2. So this is actually really useful, and we're going to talk about this. So now let's talk about 2 by 2 systems, so two equations and two unknowns. We saw last chapter, this can be written as a matrix multiplication. So we're going to talk about this later. Right now, we'll just start with examples and how you might solve them with just algebra you learn in school instead of linear algebra. So let's start with this one. 2x plus 3y is 12, and 3x minus y is 7. So you could do a lot of things to eliminate variables. We could try to eliminate x first. So we could try to make the same coefficient in front of both x terms. So right now it's 2 and 3, but we could do the following. So 3x is 3 halves times 2x. So we can multiply the whole top equation by 3 halves without changing the information. Right? If I multiply both sides of an equality by a non-zero scalar, I don't lose any information. It'll be the exact same information. So if we multiply both sides by 3 halves, we get this new equation, 3x plus 9 halves y equals 18. And we could just leave the second equation as is. But now both of them have 3x. So we could subtract one of the equations from the other one. So for example, subtracting 3x minus y from 3x plus 9 halves y. And that's the same thing as subtracting the right-hand side. So it's the same as subtracting 7 from 18. So we could do that on both sides. So we could change these two equations to a new equation, that's the result of the subtraction, and keep the bottom equation. So keep 3x minus y is 7, but subtracting the bottom one from the top one, we get a new equation, 11 halves y equals 11. And now we could solve for y right away. Y equals 2. Now we could go back to the bottom equation, plug in y equals 2, and get 3x equals 9, and x equals 3. So the solution is x is 3, y is 2. That's one way of eliminating a variable. We eliminated x first and solved for y, but we could have eliminated y first. And this actually seems easier to me because we won't need fractions. If you multiply the bottom equation by 3 and replace it, so 3x becomes 9x, minus y becomes minus 3y, and 7 becomes 21. And now you have a 3y and a 3y in both equations. We can add the two equations together and replace the bottom equation. We get 11x is 2 plus 9. 12 plus 21 is 33. And now 11x is 33. X is 3. And you could plug it back into the top equation to get y is 2. That's the same solution we had before. This one didn't require fractions, but we eliminated y first. You just have to notice which one is easier to eliminate when you do algebra. And notice that the first one we did is this kind of system where we reduced to one equation with two unknowns and one equation with one unknown. And this special case of a system, if we started with the system, for example, is very easy to solve. You just get y is 4 and plug back in to get x. It's very simple. And that's the goal of eliminating. When we eliminated up here, we got this kind of system with one equation with two unknowns and another one with one unknown. And same thing down here. We had one equation with two unknowns and one equation with one unknown. And then it was trivial to solve. So we could call this kind of system an upper triangular system if it's organized this way, right? The bottom equation has one variable, the next one has two variables, and the top one has three variables, or however many you have. With our 2x2 system, it was the bottom equation had one variable, and the top equation had two variables. So this, again, is very easy. Z is 2 already. Then y plus 4 is 6. So y is 2. So we solve for y right away. And then plug them back into the top equation to get x plus 4 plus 6 is 14. So x is 4. You're done. Very easy. All of the elimination already happened in previous work, or we didn't need it at all. So one goal to solve these equations is to do some algebraic operations, such as elimination, to reduce them to triangular systems. So having the goal in mind of reducing to a triangular system is a common one in solving systems of equations, especially for some tools in linear algebra. So this is called upper triangular. You could also do a lower triangular system, and this one up here is much closer to what is a lower triangular system, although not exactly. If we take x to be the first variable and y to be the second variable, but it's very similar. This one is actually much closer to being a lower triangular system. But the point is, it forms some triangle if you reorganize in some way. So here is a simple 3x3 system. And let's just do an example because these are more involved than 2x2 systems. So we can subtract the top row from the bottom row. You see x and x appear. So we could subtract them to get rid of x. So if you subtract the top from the bottom and replace the third row, you get this row. And then you can subtract 2 times the top row so that x and 2x will match, and subtract that from the second row and replace it. So what happened was, let me get a pen. What happened was we did x plus 2y plus 3z equals 14 minus, so we could subtract 8, and we could subtract x plus y plus 2z. So subtracting is the same because these are all equal. We could subtract the same thing from both sides. So if we subtract, we get y plus z equals 6. Oh, so I subtracted the opposite way when I wrote it. I subtracted the top one from the bottom one to get y plus z equals 6. And then we could subtract 2 times the top row from the second row. So we could do minus 2 times x plus 2y plus 3z minus 2 times 14. And this will give 0 x's, minus 3 y's, and minus 5 z's. And then 6 minus 28 is minus 22, which was this row over here. So we got rid of x from the bottom two equations. Now we reduced this to a 2 by 2 system, and we know how to solve 2 by 2 systems. You get rid of one of the variables and make it something that looks like a triangular system. But to make it easier to look at, let's get rid of these minus signs and just multiply both of those by minus 1. And let's also switch them because I think that'll be easier. So now you could subtract 3 times row 2 from row 3 and replace row 3 by that. So what we're doing is 3y plus 5z is 22. Subtract y plus z. That's the same thing as subtracting 6. Oh, sorry, 3 times. 3 times that. And we get 2z here. And on this side, you get 4. So z is 2, or 2z is 4. So this is what you end up with. This is an upper triangular system. It's very easy to solve, right? You get z, and then you get y, and then you get x. So here's another example. There's systems which have no solutions, such as when equations are incompatible, like they contradict each other. You can't have 3x plus 4y is 10 and 3x plus 4y is 11. That doesn't make sense. And if you try to do the above method by eliminating variables, you are going to get something that won't work. So you could try it yourself and see what happens. There's also equations that have infinitely many solutions. For example, if I have 3 equations and 3 unknowns, but actually it's only 2 equations and 3 unknowns. This last one doesn't give me any new information. So the only relevant ones are these two. In this case, one thing I love to do is think of it as a 2 by 2 system that depends on z. You could think of these as constants, and you could get answers for x and y. So x will be something that depends on z, and y will be something that depends on z. We could actually solve this system and see what happens. So let's solve it. If I multiply the top equation by 2, I get 2x plus 4y equals 28 minus 6z. And then I have 2x plus y equals 6 minus z. I could subtract the bottom equation and get rid of x. So I get 3y. This is an implication symbol. 3y equals, if I subtract, I get 22 minus 5z. So, and this is a 2, sorry for this writing. So I get y equals 22 minus 5z all over 3. And this is what y is, depending on z. And now I could plug back in for x. So 2x is going to be 6 minus z minus 22 minus 5z over 3. So that means that 2x is, if I have a common denominator, 18 minus 3z minus 22 plus 5z all over 3. And let's actually divide both sides by 2 and change this to 6. So I get x equals minus 4 plus 2z over 6. And you could divide both sides by 2 to simplify. So you see in this case, you could treat the system as a 2 by 2 system and just leave z and have your x and y depend on z. But this is infinitely many solutions because now z can be anything, and x and y depend on z. So these 2x3 systems are not very complicated. You could think of them as 2x2 systems and let z be part of your answer. But then you get infinitely many solutions. You could also think of 3x3 systems or systems with more than two variables geometrically. Two planes intersect in a line, and usually three planes intersect at a point because a line intersect a plane is usually a point. So when this happens, we see that there's a unique solution. When two of the planes are the same, or one of the planes doesn't give any new information, then we get a whole line of solutions. And we saw that line depended on z. We'll talk about equations of lines later on in the class. So we could also talk about substitution. That's another method, but we won't focus on that in this class. You could transform two equations into variables into one equation with one variable by solving for one of the variables. So we could solve for y in the bottom equation and plug it back into the top equation. When we plug in y is 3x minus 7, we get 2x plus 3 times 3x minus 7 is 12. And then if you work that out, you get x is 3. So you could still solve for x if you do this method. And then you just plug x back in to solve for y. And we get the same answer as we did using the other method of elimination. This method does have a context in linear algebra, but we're going to be focusing on elimination for now. So let's talk about how to solve by substitution and elimination with matrices. So we're going to build a framework for the method we discussed above using language of matrices. And the ideas of elimination in particular where we multiply some row by a non-zero constant and add or subtract it from another row. And we replace that row, we replace one of the rows we applied these operations to with the new row. So we'll see examples. And here's some new notation that we haven't seen before. So if you have an n by m matrix and an n by k matrix, so they need to have the same number of rows, you could define an n by m plus k matrix by just thinking of them side by side. Here's the formal definition, and we put a bar in between the entries just for notation. But you don't need the formal definition. The concept is very easy. So for example, if I had this matrix A and this matrix B, which is a row, or is a column vector, then we could augment the matrix AB. We just write A on one side and B on the other side with a line in between. And that's it. So let's consider the equation we solved a few times with different methods already, going back to this 2x2 system. We can write it as a matrix multiplication, 2, 3, 3 minus 1, xy is 12, 7. We're solving for xy, so x and y don't give us any information. All the information of this problem is from the matrix A and this column vector B. So all the information comes from the augmented matrix AB. Now we could perform row operations on this matrix, which we'll define, including an augmented matrix. Augmented matrix is just notation for a different kind of matrix where this divider helps us organize the entries. But it's still a matrix. It's a 2x3 matrix. So let's talk about row operations. So first, let's talk about linear combination because we need that for row operations. So let's say I have any two matrices. A linear combination of A and B is of the form CA plus DB, where C and D are scalars. And more generally, given n by m matrices, they could be column vectors, row vectors, anything at all. A linear combination is I multiply each of them by some scalar, and then I add them all. This is what a linear combination is. One special case is if the linear combination equals 0. And this could be more than a sum of two. It could be a sum of k of them. But if it equals 0, we call it a zero linear combination. And if CA plus DB is not the zero matrix, it's a non-zero linear combination. And for row operations, we want to focus on non-zero linear combinations. So here's the definition of elementary row operations. If I have a matrix M, we could define the following, a matrix M with more than two rows or more than one row. We could define the following row operations. We could multiply a row vector by a non-zero scalar and replace that row with CR. So we've done that already. If we scroll all the way back up, here, we had a row, 2x plus 3y is 12, which is now just 2, 3, 12. And we had the row 9x minus 3y is 21. Well, we had that equation, which becomes the row 9 minus 3, 21 in our augmented matrix. But this came from another equation. This used to be 3x minus y equals 7. So we took the matrix 2, 3, 12, 3 minus 1, 7. So this was, let's call this row 2. In order to get the new matrix, we replaced row 2 with, we replaced it with 3 row 2. So we took 3 row 2 and put it in the row 2 spot. So this is going to be the notation, and we'll talk more about that. But we already did this elementary row operation in order to get the same coefficient when solving for x and y in the system of equations. So let's go back to row operations. We multiplied a row vector by a non-zero scalar and replaced that row with that multiple. So we replaced R with CR. More generally, we could replace a row R with a non-zero linear combination of R and other rows. For example, you could replace R with AR plus BR prime for scalars A and B, or replace R with AR plus BR prime plus CR double prime for some other rows, R prime and R double prime. We haven't done that yet, but we did do the first one with just 2 rows already as well. So see if you can go back and find where we did that. And this is just a more general version of 1, because CR is also a linear combination of R. We could have just had 1 row. So that also works. For matrices with more than 2 rows, we can take linear combinations in general, not just with 2 or 3 rows. We could take any amount of rows. And sorry, I forgot to add this. This is what a linear combination would look like, and we replace, for example, row 1 with this combination. We could also swap rows. We didn't do that above, but this helps sometimes just to organize. So let's look at the matrix M and do examples of these operations. So if R1 is the first row of M, what we could do is take 3 times row 1 and put it into the row 1 slot. So 852 got multiplied by 3 and put into the row 1 slot. You could also do something like 2 row 2 minus row 1. So in this case, 8 minus 8 will be 0. Oh, and then 2 row 2, so that's 18, minus 5 is 13. And then 14 minus 2 is 12. We put that into the row 2 spot. So 2 row 2 minus row 1 into the row 2 spot. And we could also swap row 1 and row 2. So the notation is 3 row 1 goes into R2. It's replacing it in the matrix. So we get a totally new matrix. But the matrix represents something that we want. We want to reduce linear equations to some easier linear equations. So although we get a totally different matrix, this kind of sequence of matrices that we get, so maybe from uh, from here to here, this new matrix, M prime, or whatever you want to call it, helps us solve linear systems better. Because if this was an augmented matrix representing a 2 by 2 system of equations, from here we can see right away that x is 12 over 3. Or sorry, I guess it's y is 12 over 3. And then we could plug it back in and solve for x. So let's use this notation to show how you could translate algebra we did into matrix notation. So we had a system of equations that became an augmented matrix. If we multiply the second equation by 3, that's the same thing as multiplying the second row of the matrix by 3, this augmented matrix up here. If we add one equation to another equation, that's like adding a first row to the second row. If we replace the first equation, that's like replacing the first row. Also, a triangular system corresponds to a triangular matrix. X equals 3 corresponds to having the row 1, 0, 3. Because if we multiply this matrix, we get this 2 by 2 matrix by xy, we get x. Sorry, this 1 by 2 matrix by xy, we get x, and on the other side we get 3. On the other hand, y equals 2 is the same thing as 0, 1, 2. So this is how we know we've solved for x when we have a 1, 0 for a 2 by 2 system. And this is how we know we solved for y if you have 0, 1 in a 2 by 2 system. And this is another goal. So first, a triangular system is very good if we get a triangular matrix, but that doesn't fully give us the answers yet. It's easy to get the answers from there, but we didn't get the answers yet. To get the answers, you really need to do some row operations to reduce the n by n matrix to an identity matrix. So yeah, we call a matrix upper triangular if aij is 0 whenever I is greater than j. That means that whenever the row number is bigger than the column number, like this one, this is row 2 but column 1, it must be 0. This is row 3, column 1, so that's 0. This is row 3, column 2, so that's 0. So here's an example of a 3 by 3 upper triangular matrix. And that corresponded to a 3 by 3 system that was very easy to solve. So if we change this to an augmented matrix, then we know exactly how to solve for z, and then you could plug it back in to solve for y, and plug it back in to solve for x. And notice that diagonal matrices are special cases of upper triangular matrices. Now, we can use these ideas to work with matrices instead of systems of equations, and that's exactly what we want to do. So going back to the system we looked at a few times already, 2x plus 3y is 12 and 3x minus y is 7, we could solve this system by using elementary row operations. So when we took 3 halves of row 1 minus row 2 and replaced row 2 above in the previous solution, this is what the matrix elementary row operation corresponds to. So if we take 3 halves row 1, subtract row 2, and put it into row 2, we get this. Now we could solve for y by making sure we have a 0, 1 in this row. So as we said before in the translation, that means y is 2. So this means y is 2, and we're done with that. But now we could reduce further to identity matrix by subtracting 3 row 2 from row 1 and putting it into row 1. So the first entry doesn't change. The second entry becomes 0. And for the third entry, you get 12 minus 6, which is 6. Finally, you could replace row 1 with 1/2 row 1 to get 1, 0, 3. So this tells us x is 3. And we're done. So we can completely translate back to x equals 3, y equals 2 from here. Notice that we didn't have to write x and y every time, although we did write brackets. So you could argue that maybe it's less writing, or maybe the symbols are easier to write than a linear system, but it's the same exact work. Here's a much more involved example. It's a 3 by 3, and I didn't choose these numbers to work out nicely. These are just some random numbers plugged in, right? It's just numbers 1 through 9 and 7 through 9. So the goal is to make an upper triangular matrix. So we want to get rid of the 3 and the 4. We want to have leading zeros. So I can have a 0 in the bottom column in the first, sorry, in the bottom row in the first column. If I do 4 row 2 minus 3 row 3. So 4 row 2 is 12, 28, 4, and 12. And 3 row 3 is 12, 18, 27, and 27. So if I subtract them, I get 0, 10, minus 23, minus 15, which is exactly what's written over here. So, oh, I'm sorry. It is written there, but more relevantly, it's written here. So we took 4 row 2 minus 3 row 3 and replaced row 3, and we get a leading 0. So that translates to not having an x in our equation. Now I want to have a leading 0 over here as well. And to do that, I computed 3 row 1 minus 5 row 2, and I put it into row 2. Right, so it's kind of like finding a common, a lowest common multiple. So we found the lowest common multiple of 5 and 3, which was 15, in order to get rid of the leading 3 in the second row. So just to write it out, 3 row 1 is 15, 6, 24, 21. And 5 row 2 is 15, 35, 5, 15. And if I subtract them, I get 0, minus 29, 19, and 6, which is exactly what's written here. Okay, so now the bottom two rows have leading zeros. The row starts with a 0. I want to now have a 0 in the 3, 2 entry, and that'll help me solve for z. Right? This will make the matrix upper triangular. To do that, again, I find the lowest common multiple, which is 290. So I replace row 2 with 10 times row 2, and I replace row 3 with 29 times row 3. Now I could add the rows and put them into row 3 to get a leading 0. And then I get some complicated numbers. To finish solving for z, I could divide the last column by negative 477, and I get a 1. And also, just to make it simpler, let's also have a leading 1 in the second column by dividing by 290 and minus 1. So I get minus 19 over 29, 6 over 29. I get these numbers. You could just check with a calculator. And then to solve for y, I could add 19 over 29 row 3 to row 2. And these are the numbers I get. Finally, I could get rid of the 2 and the 8 in the first row by taking a linear combination of 3 vectors. If I do row 1 minus 2 row 2 and minus 8 row 3, that will give me 5, 0, 0. And if you do all the subtraction, you get 5 over 53, as the 1, 4 entry of this matrix. Finally, to solve for x, divide the top row by 5. So that's it. We used row operations to obtain an upper triangular matrix, and then we took it further by reducing the matrix to identity matrix, from which we can read off completely all of the solutions. Z is 125 over 159, Y is 49 over 159, and X is 1 over 53. Again, these were just random numbers, not made to work out nicely in any way. Try some examples yourself.